asked us to find, wait, I'm going to zoom in. So find the spring constant of the bimetallic bar. Okay, they want us to find the spring constant of this whole bimetallic bar. But we know that this two is made of different materials. The upper the upper bar is made of steel and the lower bar is made of aluminium. Okay, so basically they are going to have a different value of stiffness because their Young's modulus is different. But if you look carefully, you'll see that this bimetallic bar, both of these bimetallic bar, the steel at the top and the aluminium at the bottom, the size, okay, the size is exactly identical. All right, the length is the same, the width is the same, and the height also is the same. The cross-sectional area, the dimensions, everything is the same, just that their materials are different. All right, so different materials will have different Young's modulus, as you can see in the figure given. All right, so oh, by the way, for those who still didn't have the textbooks, I'll send this module inside the what do you call that, Microsoft Team after this. So first of all, how are we going to find equivalent K? Okay, two different stiffness for two different materials, but they are bimetallic bar, right? So how are we going to find the equivalent K, the total stiffness? Okay, first of all, we have to derive. Okay, first of all, we have to derive the strain. Sorry, we have to derive the strain. Okay, I'm going to zoom in now. So first of all, the strain. Okay, epsilon is strain is defined by the symbol epsilon. Okay, if you still remember mom. So strain of, since they are basically identical, all right, identical in dimension, so their strains are the same. So the strains for S, which is the steel, is equivalent to the strain of the aluminium, which is the A. All right. So basically, the formula for strain is actually X over L, where the L is length and the X is elongation. Okay, elongation. So remember, this bimetallic bar is undergoing the axial motion, right? Axial motion. So there will be elongation to the bar. So remember, the formula for strain is strain. So the formula for strain is X over L, which X is the elongation. So since both having the same dimensions, the strains for both materials are also the same. So what else? Okay, so now I'm going to further expand the strain. So the formula for strain also have another formula. So strain equals to stress over Young's modulus. All right, strain equals to Young's, strain equals to stress divided with Young's modulus. So I'm going to do the same for both steel and also aluminium. All right. So this is just basically a basic derivation. And then next, I'm going to separate these two because it's quite confusing to see it this way. So I'm going to separate them. So basically, stress over Young's modulus equals to X over L. For both, right? So I'm just going to separate them and aluminium with the formula X over L. Okay. Now, so from here, we basically want to find the stress. So the stress will be, if I want to stress, so the stress will be, I have to bring the Young's modulus to the other side, so it will be like this. You guys understand? Okay, because I want the stress now. So stress for aluminium will be Young's modulus of the aluminium times the elongation divided with the length. So I already have the formula for both aluminum and steel in terms of stress. Now I've already derived this formula. So next we have to find the total axial force. Total axial force. So we know the total force is basically this is axial force, huh? So axial force for total axial force will be axial force for steel plus with the axial force from aluminium, right? Total force. There's only two materials, so there's only force for steel and also force for aluminium. So another formula that you guys have to know, force also equals to stress times cross-sectional area. All right. So the axial force for steel equals to stress of steel times the area of cross-sectional area of the steel. Same goes for the aluminium. Stress for aluminium multiplied with the area for aluminium. Cross-sectional area for aluminium. We do know the values for the area for both because we already have all the dimensions, right? But we don't know the one thing that we do know is the stress. So that's why we try to derive just now to find the stress so that we can substitute the stress so that we don't have to find the stress. We just use the formula we've already derived. So substitute this both into this. Okay, basically the same thing, just substitute. So this one you get Young's modulus for steel times the elongation over L. Also this stress for aluminium, use this, substitute. Young's modulus for aluminium times x divided times the elongation divided by length, and then times with the cross-sectional area for aluminium. Sorry. Okay, so since we do know that, all right, we do know that the force, okay, the force. Also, we want to find what do we want to find? Spring constant, right? So what is the force for spring? Can anybody tell me what is the force of a string? A string pula. Sorry, force of a spring. F equals to for spring. F equals to kx, right? So I'm going to put here F equals to kx. All right, since we want to find that is actually the total force, right? So total force equals to the total stiffness times the elongation lah. So force equals to kx, F equals to kx. So we're just gonna write everything down. So we can cancel one thing now because we don't know the elongation, right? The question just give a simple diagram with the dimensions and the value of Young's modulus. And then they wants us to find the value of a spring constant, the equivalent K basically. So we don't know the elongation, so that's why we substitute F with the Kx so that we can substitute all the elongation because the elongation will be the same, right? So X, you can cancel them out. So you'll be left with this one particular formula here, which is K, equivalent K equals to ES AS over L plus EA AA over L. All right, understand this? So, and then just to make your life easier, as you can see that the length for both material and the width and also the cross-sectional area for both material is the same, right? Because their dimensions are exactly identical. So meaning, all right, meaning cross-sectional area for steel and also cross-sectional area for the aluminium is basically the same, right? So since cross-sectional area and also the length are the same, we can factorize them out to be A over L. just A. All right, you don't have to define it as A for steel or A for aluminium. And then once you factorize that, you'll be left with what? ES plus with EA. Once you factorize A over L. Sorry. Young's modulus for S plus the Young's modulus for aluminium. All right. So now if you want to find the value for the spring constant, we can actually, because we've already have all the values. All right, we've already have all the values. So we've already have the values for A, we've already have the values for L, and both of the materials Young's modulus. So try to substitute first before while I'm calculating. You can try to find the value. Try to substitute the cross-sectional area, the length, and also the Young's modulus for both materials. So A equals to, remember, if you are trying to substitute any values, you have to know that you have to always make sure that if you are substituting the SI unit, okay, the values in the SI unit. So for example, here given in cm, so you have to always convert to meter before you substitute. So area will be 2 cm will be 0.02 meter, 0.5 cm equals to 0.005 meter, right? Only then you can find the cross-sectional area, this one. So basically 0.02 meter times 0.005 meter. That's cross-sectional area, right? Divided with the length is 0.5. And then multiply with the summation of both materials Young's modulus. So Young's modulus for the steel is 207 times 10 to the power of 9, plus with the Young's modulus for the aluminium is 83 times 10 to the power of 9. So if you calculate this, your equivalent K, you'll get it to be 5.8 times 10 to the power of 7 Newton per meter. All right, so that's the answer for this question.